Good morning, ladies and gentlemen. May I have your attention, please? Thank you. As you'll notice, today we'll be recording our class period. Today, I don't know if you guys have noticed, but the Twitter boards have been going off. People have been complaining about not having a B-Day recording, so they want to be on the recording. And so today we're going to record our 2B Advanced Algebra because I know there's been a lot of backlash with only having the A-Day recordings back up. And so I'm not going to mention any names, but let's go ahead and get to it. So we need to be able to solve a quadratic equation regardless if there's x squareds and x's mixed together. We know that taking square roots is not a viable option if we have both an x squared and an x term in the same problem. So I'm going to go ahead and add or subtract, get everything on one side set equal to 0, and try to factor. If, after adding, subtracting, and putting in standard form set equal to 0, I can't factor, then I'll go ahead and solve by completing the square. But I'm always going to try to factor first because I think that's more efficient. And so my best first step here would be subtract 3x from both sides. After rearranging in standard form, I'll now go ahead and try and factor. So I'll consider my factors of the first and my factors of the last when placed in my binomials that create an outer product and inner product that sum to give me that middle term -3. So let's see if we can set up our parentheses. Because our first is 2x squared, I know that my variables won't just be x and x, but rather 2x and x will be my first product to create that 2x squared. I also know that my last, positive 1, is going to come from 1 and 1. There's no other integers that will multiply together to give me that 1. And now I'll go ahead and consider the signs. Go ahead and help me out when I call on you. Is the constant term in my blue trinomial, is the constant term positive or negative? Ben? Positive. So does that tell me about my binomial signs? Are they going to be same or different, given that I have a positive constant term? Will be they same or different? Grant? Same. Given that they're the same, thank you, are they both going to be positive or both going to be negative if my middle term is -3x? So are they going to both be positive or both be negative? Jacob?
Negative.
Both negative, thank you. So we can go ahead and fill these in and check our outer and inner product. So right now I'm going to check my outer product. 2x times -1 is -2x. When combined with my inner product, -1x, does that give me the -3x? Yes, it does. So I know I factored it correctly. Now that I have fully factored form set equal to 0, I can utilize the zero product property and set each individual factor equal to 0 and solve separately. So let's go ahead and do that. We'll go ahead and set that first factor equal to 0, set that second factor equal to 0, and then solve separately to generate my potential solution values. In the first case, it looks like I'll add 1 to both sides to isolate the variable term. 2x equals 1. Let's finish it out by division. X equals 1/2 is one potential solution value. In the second case, it looks like I can solve in one step. Simply adding 1 to both sides gets my variable. Now let's go ahead and raise your hand if you had x equals 1/2 and x equals 1. Who had both of those? Keep your hand up if you know how to check. Right? How can we check and see if those are correct? Thanks, hands down. April?
You plug in the number in the equation.
Absolutely. We could plug these numbers, these potential solution values, in my original equation and see before we did anything and see if it makes a true statement. So let's go ahead and try with the 1. That'll be easy to check. 1 in for x squared is 1 times 2 is 2. 2 plus 1, does that equal 3 times 1? Yes, it does. 2 plus 1 equals 3 times 1. So I know I found one solution. Let's go ahead and check with the 1/2. X equals 1/2. That'll be a little trickier to check, but I know we can do it. 1/2 in for x squared would be 1/2 times itself. So 1/2 times 1/2 is 1/4. 1/4 times 2 is 1/2. 1/2 plus 1 is 1.5. Does 1.5 equal question mark 3 times 1/2? 1.5 equals 3 times 1/2. 1.5 equals 3/2. So yes, we found both solutions, and we know that there's no more hiding out there because this is a quadratic equation. A degree 2 polynomial means there's at most 2 distinct solutions. Awesome. What questions do you guys have about number 1? Okay, in order to be successful solving number 1, we had to be good factors, right? We had to be good factors in order to solve that because we had a leading coefficient other than 1. We didn't just have a 1x squared, right? We need to have a 1x squared if we're going to be able to solve by completing the square. So that was the key feature with number 1. Let's take a look at number 2 and make sure we accomplished our content objective from last time. That was to create a quadratic regression, a parabola of best fit given data points. And so we can go ahead and enter our x values into list 1. So we'll put our x's and enter those into list 1 in my stat edit menu. we'll go ahead and input our y's. We'll input those into list 2. So we go stat, edit, and in the interest of time, I've already entered my x values in there for list 1. I've entered the corresponding y values in there for list 2, and we want to make sure that those match up. And so it looks in each case that we have the same number of x's and y's, so we avoid a dimension mismatch error from our calculator. After we've entered our x's in list 1 and our y's in list 2 by using stat edit, we'll go back to the stat menu, but this time select calculate. So we'll stat, right arrow, calculate, and we want the 5th option, quadratic regression. So we'll go ahead and grab quadratic regression, take a screenshot of that. Now, a great time saver, right, and also to make sure that you don't lose any accuracy, is to, instead of pressing enter right away, store your regression equation in your y equals menu, in your function menu for y1, and then you don't have to worry about copying down all those decimal places, right, or typing incorrectly. And so what I always do when I go to do my quadratic regression, before I do my final answer, I go ahead and store my regression equation in the y1 menu. How do I find that? Everybody, bars, y bars, function, y1, enter, and then I'll go ahead and calculate the regression equation. I'm telling the calculator where to store it. Now, if you have classic type, you won't see this x1, x list L1 and y list L2. You won't see all that. You'll still press the same exact keystroke. You'll do quad reg, and then it'll be, before you press enter, you'll do bars, y bars, function, y1, enter, and then when you press enter, finally to calculate, it'll automatically store this regression equation that it spits out the values for A, B, and C into your y equals menu. So when I go to y equals, voila, I see it already has those values of A, B, and C entered in there. And look, it kept all the decimals, so I don't lose any accuracy. That's pretty powerful. All right, what I'm dying to know is how good of a job this does. So first, I'll write down my answer that the calculator gave me. I still need to write down the equation. So what will I write? I'll write y equals opposite of 0.011 x squared plus 1.060 x, and I'm keeping 3 places here, plus 0.242. Raise your hand if you generated the same decimals for your quadratic regression. Did you get the same decimals? That means you were able to use the stat menu correctly. Way to go, you guys. So after I generate the equation, as an additional note, I want to go ahead and see how this parabola fits my original data points. And so to do that, we could go up arrow to plot 1 and turn it on. So I'm going to go ahead and up arrow to plot 1 and turn it on. So if I turn on my plot 1, right, then I'm going to see the scatter plot from the x comma y values I entered in my stat list 1 and list 2. And I'm going to see my graph of the y equals. I'm going to see the parabola and see how good of a job it does approximating the trend exhibited by those graph data points. However, first I need to make sure that I have a good window. And so to do that, I'll consider the values of my initial points. It looks like my x's span from 7 to 67, so I want to go past on either side. I'm going to go maybe negative 10 to 80. I want to go past on either side so I get a good window. So I'm going to go ahead and do negative 10 for my x min and 80 for my x max. I don't know if that's going to be a good window, but I'm going to try, and I'll manually adjust it later if needed to. My y's look like they span from 8 to 26. Did you guys get that? 26 is my maximum. So I'm going to go negative 20 to 50. I'm going to go negative 20 to 50. Now, you may do a slightly different window, right? You can do a different window, and we'll see if yours compares well or not, and we can always adjust it. We don't know until we take a look. So let's go ahead and see what that looks like. There's my scatter plot in red, and here's my model in blue coming through from the quadratic regression. How do you think that parabola does, right, fitting the data from the points? Do you think that does a good job or a bad job? Grace?
Good job.
A good job. It appears as though the trend, right, the trend is followed fairly closely by the parabola. So while it doesn't hit the points exactly, we wouldn't expect it to if this is real-world data. which is typically messy. What we're trying to do is find a model that approximates the trend, that does a good job kind of following where that trend lies. And so I think it does a good job as well. Thank you, Grace. I'm going to take a screenshot of that because we're striving for PDFable, comma baby. Awesome. All right, let's go ahead and switch gears then. At this time, I'd ask that you take out your assignment number 5. You've already shown me your reading questions. I'm going to go ahead and pause the recording while we do our homework collection, and then we'll resume. Thank you. A quick reminder that you must attend one of the FST/pre-calculus compacting meetings if you'd like to apply for that. The vast majority of you are going to continue, if you're performing well in advanced algebra, are going to continue on and take the regular FST course next year. If you're a current junior, remember you could check out senior algebra if you might be interested in attending a tech school and get dual enrollment credit. So you can get college credit and high school credit at the same time, so that's nice. And then we talked about these other options in length on other class grades, and so we're going to go ahead and continue. As always, if you have any questions about your possible options, you can certainly ask me outside of regular class or your first semester advanced algebra teacher if you didn't have me, because they'd have a better handle on where you are kind of in your mathematical careers, but certainly don't hesitate to ask me questions if you haven't. All right, so when given a standard equation, right, ax squared plus bx plus c, a quadratic equation in standard form, when is it most efficient to solve by taking square roots? And we've done this, right, for several days now. Today I'm going to focus in on our variables, our parameters, a, b, and c here, and see if we can't streamline our reasons a little bit. If we're in standard form, ax squared plus bx plus c equals 0, in order to solve by taking square roots, remember we've said time and time again that we can only have a single squaring term. If we're in standard form, that would mean that the value of b would have to be 0, right? So that I just have an x squared term. So a quick reason, if we're in standard form, for why it's most efficient to solve by taking square roots is if b equals 0. Right? If b equals 0, then what would happen to this linear term here in the middle? It would disappear, right? Because 0 times x, we wouldn't have an x term. We wouldn't have a linear term if b equals 0. So it's most efficient to solve by taking square roots. If I'm in standard form, if p equals 0, then there's no linear term, right? There's no linear term. So then it's most efficient to solve by factoring, right? It's most efficient to solve by factoring if b doesn't equal 0. That is, there's both an x squared and an x term in the same problem, and I'm already in standard form, set equal to 0, then it makes sense to try and factor. And so, for a good reason, a short reason for number 2, b doesn't equal 0. So if b doesn't equal 0, then I'll put it in standard form and try to factor. It means there is a linear term. I'll try factoring as a means for solving. And finally, if I'm unable to factor it, but I still have an x squared and an x term mix, that is b doesn't equal 0, right? But I can't factor, then I'll use completing the square. That's kind of the last thing on my list. I'll try factoring first because I think it's more efficient. Then if I can't factor, then I'll go ahead and do completing the square. That's a little bit more involved because I've got to get my x's on one side with leading coefficient 1x squared, take half the magnitude of the middle term, square it, and add that special number to both sides to play completa, and then go ahead and rewrite that perfect square trinomial I just created as a binomial squared. That's kind of okay. That takes longer, right, than just factoring. Unless we can't factor it, then I'm going to go ahead and complete the square. So what can we say for a reason? B doesn't equal 0, so there is a linear term, but I can't factor. And remember, maybe it's unfactorable, right? So it's not possible to factor it, or maybe we're bad at factoring, or maybe we don't recognize the factors. Then completing the square is certainly a viable option. Awesome. Today we're going to extend our discussion to include a fourth method for solving quadratic equations, and that's going to be easier than completing the square and handle a wider variety of quadratic equations. For that reason, it gets its own name, the Quadratic Formula, and that's what we're going to generate and apply today. We're also going to make an explicit connection between the pieces of my Quadratic Formula algebraically and the graph of the parabola, so I'm super excited about that. So if we wanted to solve this, 2x squared plus 6x plus 10 equals 7, Do I have both the quadratic and a linear term in the same problem currently? Cameron? Yes, so can I solve by taking square roots? No, if I've got x squared and x mixed in the same problem, then I can't solve by taking square roots. So I would get in standard form, everything on one side set equals 0 and try to factor. So if I first subtracted the 7 over and rewrite in standard form set equal to 0, I get 2x squared plus 6x plus 3 equals 0. Then I try to factor. So I'd go ahead and set up my parenthesis pairs for my binomials. And I consider my factors of the first. I know that's 2x squared. So my choices for the first must be 2x and x. Then I consider my factors of the last. In this case, my factors of the last include plus or minus 1 and 3. Because I have same signs, right? Because my last term is positive, I know that I have same signs for my binomial, and given that they're the same signs, if my middle term was positive, then they must be plus, plus. However, as I consider this placement and the resulting outer and inner products, let's see what we get. So my outer product would be 6x, my inner product would be 1x. Does that sum to give me my middle term? No, that would give me 7x. So let's switch the 1 and the 3. So we switch the 1 and the 3, and now what's my outer product? Well, now my outer product is plus 2x. My inner product is plus 3x. Does that sum to give me my 6x? No, that gives me 5x. And so what have we learned? Well, there's no other placement for 3 and 1. And there's no other placement for 2 and 1. And so I cannot factor this, which means we have to do what? Yes, that's right. We have to complete the square. However, in order to complete the square, we need all the x's on one side and everything else on the other with a leading coefficient of 1. So what would we do? Well, we'd go ahead and subtract that 3 right back over. We'd subtract 3 over now to get the x's on one side and everything else on the other. In order to complete the square, we need a leading coefficient of 1 on my x squared term. And right now my leading coefficient is 2. And so what would we do in order to get a leading coefficient of 1? Well, we'd have to first divide both sides, each term by 2, to force that leading coefficient to be 1. After doing that, we go ahead and reduce. I get 1x squared plus 3x, scooch the equal sign to make room for my favorite game, the complete the game, and then minus 3/2 still on the right. So now we need to find that magic number, the special number that I'm going to add to both sides that will create a perfect square trinomial that allows me to rewrite in a binomial quantity squared, a single variable x term squared, and then I can solve by taking square roots. In order to do that, remember our strategy. We considered the magnitude of my middle term, in this case 3. What's half of 3? 3/2, and then square it, and that's the special number I add to both sides. So 3/2 squared would be 3/2 times 3/2 is 9/4. So I'd add 9/4 to both sides. However, because I divided both sides by 2 already, not only did I have an odd middle term, I also created a fraction over here on the right. Now I'm combining that with another fraction. Do you guys see that solving by completing the square, though possible, is kind of a pain? So what I'm going to do now is unprecedented. Yes, that's right. I'm going to go right here and I'm going to say ... Yes, we could continue going. We could continue grinding this out and get our solutions, but completing the square is difficult in this case because two things. We have a leading coefficient other than 1, and we have an odd middle term, right? Once I get a leading coefficient of 1, both of those are bad news if I'm trying to solve by completing the square because it creates an inordinately difficult problem. In fact, this is much easier using today's quadratic formula. And so we could use completing the square once and for all to solve the standard equation ax squared plus bx plus c equal to 0 for x. And in doing so, generate the quadratic formula, which will always, always work. This provides me a means to solve for my solutions x simply by identifying the values of a, b, and c for my standard form quadratic equation, plugging them in, and working them out. this is going to save time and energy. And so the quadratic formula is a big positive, and it'll easily handle ones that had a leading coefficient other than 1, like that 2x squared, and an odd linear term, like that 3x. So quadratic formula is the way to go if I can't factor, okay? And it surpasses completing the square in my list, all right, of favorite methods for sure. You must memorize the quadratic formula. And so you have to memorize the quadratic formula. One of the Common Core state standards is that students need to be able to solve quadratic equations of various types, including the use of quadratic formula. That means we need to be able to solve using the quadratic formula. And I think after we do couple together, you guys are going to like this method better than completing the square. I know I do. So let's go ahead and check out the formula and see how it works. X equals opposite of b over 2a. Plus or minus the square root of b squared minus 4 times a times c, closed radical, all over 2a. Equivalently, and lots of textbooks have it this way as a single fraction, opposite of b plus or minus square root of b squared minus 4ac, all over 2a. Both of these are equivalent and correct. It's just we're going to focus in on this left one today when we make a graphical connection between the different pieces of that formula and the graph of my parabola, y equals f of x. And so that's where we're headed. If you're concerned about memorizing it, in fact, on your Unit 6 test, there's 2 parts again, the non-calculator portion and the calculator aloud. The non-calculator portion has a question where you just have to state the quadratic formula with a, b, and c, right, correctly for points. So you have to memorize this, and you'll get some easy points if you memorize it on your non-calculator portion. On the calculator aloud, you'll be given the formula, and then you'll have to be able to apply it. So today we're going to practice doing both. I want you to know that if you're concerned about memorizing it, don't worry. At the end of today's class period, we're going to watch a little clip of Emily, our very own Emily, right, who memorized it and is going to share that with you as well. So we'll check that out a little bit later. Not only will the quadratic formula help you solve any quadratic equation, it'll also tell you many useful things about the graph of the parabola. Okay, so that's what we're going to investigate today. Everybody on your note sheet, let's go ahead and find your x squared minus 4x minus 12 equals 0. Let's solve this, right? Let's solve this using quadratic formula to practice. I know we could solve this using different means. It looks like I could try factoring because I'm in standard form. I could also solve by completing the square pretty easily because I have 1x squared and I have an even linear term. That negative 4x is even, so I could solve this using factoring or completing the square. The reason we chose it, however, was so we could practice our new way, quadratic formula, and then we could always compare it with one of the other methods. And so let's go ahead and choose our values of a, b, and c based on this original problem. I'm already in standard form. The quadratic formula only works if we're in standard form set equal to 0. I'll go ahead and pick out my values of a, b, and c by looking at my original equation. It looks like ax squared, a would have to be 1 in that equation to be 1x squared. B in this case is negative 4, right, because it was x squared minus 4x, so you need to grab the negative. And lastly, the value of c is negative 12. Once I have the values of a, b, and c, all I need to do is plug them into this formula and evaluate it. It'll tell me what x equals. X is already solved for. So all I need to do is plug and chug. Let's go ahead and do this first one together. I'm going to go ahead and start out with my quadratic formula. X equals opposite of b over twice the value of a plus or minus the square root of b squared minus 4 times a times c closed radical all over 2a. And I'm going to rewrite this, but now I'm going to substitute in my values for a, b, and c. So opposite of b over twice the value of a plus or minus the square root of b squared is always positive minus 4 times a times c closed radical all over twice the value of a. Except everywhere I see an a, I'm not going to put a, I'm going to put 1. So we're going to substitute in 1 for a. Everywhere I see a b, I'm not going to put b, I'm going to put negative 4. So we'll plug in negative 4 everywhere I see a b. Keep in mind that this b squared is always going to be positive, right? So I'm putting negative 4 in for b, but I'm putting it in parentheses. When I square that, the result will be positive. And lastly, everywhere I see a c, I'll put negative 12. Now let's go ahead and evaluate this expression. So here we go. We're just going to evaluate it. So we'll start working it out. X equals opposite of negative 4 is positive 4 over 2 times 1 is 2 plus or minus. Let's jump inside the radical. I know that negative 4 quantity squared is 16. Negative 4 times negative 12 is positive 48. Close radical. All over twice the value of a is 2 times 1 is 2. Now we'll go ahead and reduce. X equals 4 halves is the same as x equals 2, plus or minus, and let's jump inside the radical. Inside my radical, I'll have 16 plus 48 is 64. Close radical, and that's all over 2. Keep the party going. I now get x equals 2 plus or minus, and let's reduce that square root. The square root of 64 in this case reduces to an integer. What's the square root of 64? Alejandro?
That would be 8.
8, thank you. Close radical over 2. Now we'll go ahead and simplify one more time, and I'm about to see what my solutions are. I know that 8 halves reduces to 4, and it appears as though my solutions are given by x equals 2 plus or minus 4. How many solutions does this represent? How many solutions are there? There's 2 solutions. One is gained by starting at 2 and adding 4 to it. The other is gained by starting at 2 and subtracting 4 from it. So what I'm going to do, just like we've done time and time again with solving quadratics, is break it up into 2 separate paths, just to drive home the fact that there's 2 separate solutions, and this is how I get there. X equals 2 plus 4 in the first case. In the second case, x equals 2 minus 4. So my solution values are x equals 6 in the first case, and x equals negative 2 in the second case. I know, right? April told us that we could plug these potential solution values up into my original equation before we did anything and see if it makes a true statement. And we could do that right now. Except on our very first day, we made a graphical connection between these x value solutions and the picture of my parabola. So what I want you to know, what I want you to do right now is go ahead and tell your partner what the 6 and negative 2 have to do with the graph of the parabola, y equals x squared minus 4x minus 12. Go ahead and remember, talk quietly with your partner and tell your partner what x equals 6 and x equals negative 2 have to do with the graph of my parabola, y equals f of x. Go ahead and tell your partner, and then I'll call on you to share with the whole class. What would those have to do with the graph? Okay, what do those x values, 6 and negative 2, have to do with the parabola at all? What do those have to do with the parabola? Hannah and Elena? The x-intercepts of the graph? All right, let's go ahead and check and see. Thank you. Let's go ahead and check and see. If I were to look at a picture, by golly, those x values, x equals, what do we say, 6 and negative 2, should be x-intercepts of the graph. Let's check. If I start at the origin and count 2 units to the left, there I am at x equals negative 2, and that's an x-intercept of the graph. If I started at the origin and counted 6 units to the right, I'd end up at an x-intercept of the graph. Way to go. Thank you. So graphically, we could check as well. Right? Graphically, we check as well. Awesome. Let's go ahead and fill in some other key characteristics, like the y-intercept. And so as I look at this picture, it appears as though the y-intercept always is the value of y where my graph crosses the y-axis. In this case, it looks like it happens at an integer, so I can actually count it out. It looks like negative 10, negative 12. Are you guys seeing negative 12? So as a point, x comma y, that would be 0 comma negative 12. Does anybody see where that y-intercept comes from in my original equation? Does anybody see where that y-intercept is hiding in my original equation? Elena?
It's the value of c.
Absolutely. That constant, the value of c in standard form, is the y-intercept always. And so as long as I'm in standard form on one side set equal to 0, the value of c is always the value of my y-intercept, the y-coordinate of my y-intercept. And so there it is, right there. And so in general, the y-intercept of my quadratic equation, the y-intercept of my parabola rather, is given by 0 comma c. So long as I'm in standard form, ax squared plus bx plus c. Next, state the axis of symmetry. Well, the axis of symmetry is the vertical line that divides my parabola into 2 equal left-right halves. And so if we could draw in a vertical line here, such that it cuts the parabola into 2 left-right even halves, it looks as though it would cross through, x equals, what does that look like? X equals 2? Does that look like x equals 2? Divides the parabola arms into 2 mirror images of one another. If I were to fold the parabola along that axis of symmetry, then the arms would fall upon itself, right? They're mirror images of one another. So the axis of symmetry is a vertical line. That's a special equation, x equals. And the x-coordinate of every single point on that vertical line would be x equals 2. And so my axis of symmetry is x equals 2. Awesome. Next, let's go ahead and state the distance between the axis of symmetry and the x-intercept. And so everybody, right, we'll go ahead and jump on the x-axis and let's pretend you're a math woman. And if you're a math woman and you're on the x-axis standing at the axis of symmetry, how many units would you have to walk until you got to an x-intercept? So let's count. We'd have to walk 1, 2, 3. Looks like we'd have to walk 4 units to get from my axis of symmetry to an x-intercept. Let's go ahead and check the other direction. So here we are, if we're math woman, and we start at the, is it the same distance? If we start at the axis of symmetry and walk to the left, 1, 2, 3, 4, then we end up at an x-intercept. And so the distance between the axis of symmetry and the x-intercepts in turn is 4 units. So Elena recognized the y-intercept value, that y-coordinate of the y-intercept negative 12, as the value of c, in my original equation. In the quadratic formula, does anybody recognize the axis of symmetry and the distance number? The axis of symmetry and the distance number? Well, if we were a math woman and we started at x equals 2 and walked 4 units to the right, we'd get to one x-intercept. So we were at x equals 2, and we walked 4 units to the right, and we got to x equals 6. Look at that. If we started at x equals 2 and walked 4 units to the right, that's the solution right here. Right? So my axis of symmetry must have come from this 2, which came from that opposite of b over 2a term. Right? The distance comes from that big radical. The b squared minus 4ac closed radical all over 2a, that fraction, that represented the distance. That was the 4 units. The math woman walked to the left or to the right to get to my 2 solutions. We'll go ahead and summarize that a little bit later. For now, let's go ahead and keep going with our x-intercepts. We already saw those as 6, 0 and negative 2, 0. Those were the x equals solution values that the quadratic formula spit out, that gave us at the end. And so these were the x equals solutions. Exclamation point. And you guys already knew that. In fact, you shared with that, Hannah shared that before we went to write down our physical characteristics. And lastly, the vertex. My vertex is, for the parabola, is the maximum or minimum point. It's the turning point, right? So it's either the top of the peak in the case of an upside down parabola, or it's the bottom of the valley in the case of a right side up parabola. So my vertex is this special point here where the parabola switches direction. That's called the vertex. In order to find the vertex, right? In order to find the vertex, I'm going to go ahead and use the fact that that vertex falls directly on my axis of symmetry. So my axis of symmetry we already saw was 2. So the x-coordinate of this vertex is 2. And now we have to figure out the y-coordinate, right? The y-coordinate. How would I figure out the y-coordinate of my vertex? Well, I know that the y-coordinate corresponds to an x value, an x input value of 2. So if I have the function rule, I could simply evaluate my function rule at x equals 2 and see what corresponding y-coordinate is. Then we could visualize, right? We could visually estimate and see if we were correct by looking at the picture. So first, let's do it algebraically. I'm going to go to my function rule, y equals. And I'm going to substitute in the x value, 2, everywhere I see an x and work it out and see what we get. Then I'll compare it visually with my graph. So everybody, let's go ahead and plug in my x value 2. I'll plug in 2 everywhere my function rule accepts x's and work it out. I get 2 squared is 4, minus 4 times 2 is minus 8, minus 12. I evaluate and get negative 4 minus 12 is negative 16. I'm getting negative 16. Are you guys getting negative 16? How does that compare visually? So does negative 16 look about, and you guys have it in your paper, Michael? What does the y-coordinate appear to be for my graph?
I have no clue, sorry.
Now, take a look at your picture on your paper. If you look at the vertex, all right, just count out the hash marks. What does the y-coordinate appear to be? Negative 16, I'm down. So I'm thinking negative 16 is the y-coordinate of the vertex. So how do we find that? Well, we took our axis of symmetry value, my x equals opposite of b over 2a, and I plugged it into my function rule and evaluated it, and that gave me the y-coordinate. So we're going to summarize that after our next one. Let's go ahead and take a look at another one then. So we've got now x squared plus 8x plus 7. First, we'll solve by using the quadratic formula. I'm going to call on you to help me out. So last time I got my parameters a, b, and c. Now I'm going to call on you to help out. So we must be in standard form set equal to 0 for the quadratic formula to work. Okay, so we have to be set equal to 0 before we can pick out our values of a, b, and c. Otherwise, it won't work. Be ready to share with the class when I call on you. All right. So what am I going to use for the value of a in this one? Right? What am I going to use for the value of a? Derek? 1, thank you. What will we use for b? Abby? 8, thank you. And what will we use for c? Ryan? 7, great, thank you. Now we're going to plug those into my quadratic formula everywhere I see a, b, and c and evaluate. And so I know that x is given by the opposite of b over twice the value of a plus or minus the square root of b squared minus 4 times a times c closed radical all over twice the value of a. And now we'll go ahead and evaluate by substituting in my values of a, b, and c that you told me. So opposite of b over twice the value of a plus or minus the square root of b squared minus 4 times a times c closed radical all over twice the value of a. Except everywhere I see an a, we're going to put 1. Everywhere I see a b, we're going to put 8. And everywhere I see a c, we're going to put 7. Now there's nothing to it but to do it. We need to simplify that expression and see what we get for our x values. So the solutions to the quadratic equation, the x-intercepts of my graph. So let's go ahead and evaluate. Here we go. Opposite of 8 over 2 times 1 is negative 8 halves. Plus or minus, let's jump inside the radical. 8 squared is 64. Negative, so minus, so that looks like minus 28. Close radical. All over 2 times 1 is 2. Next, x equals negative 8 halves is negative 4. Plus or minus. Let's jump inside the radical. 64 minus 28, that's, carry the 9 square root, 36. Is that 36? Close radical, all over 2. So I'm getting x equals negative 4 plus or minus, the square root of 36 is 6 over 2, 6 halves. And then we'll keep the party going. So I'm getting x equals negative 4 plus or minus 3. How many solutions does this represent? 2. What are they? They're given by negative 4 plus 3 in the first instance, and they're given by negative 4 minus 3 in the second instance. So again, I'll go ahead and split it up to be consistent with our earlier designations. We're going to get 2 different answers here. One comes from taking negative 4 and adding 3 to it. One comes from taking negative 4 and subtracting 3 from it, so we get x equals negative 1 and x equals negative 7. Visually, we would expect negative 1 to be an x-intercept value. Negative 1 comma 0 should be an x-intercept. Negative 7 comma 0 should be an x-intercept. Algebraically, we would expect these values when substituted in my original to work out and make a true statement. Either way we can use to check, but because we're making our graphical connection, we'll go ahead and check our picture that you guys have. All right? Our picture looks like, by golly, negative 1 comma 0 is an x-intercept. Hooray! Negative 7 comma 0 is an x-intercept, so I'm confident in our solution. Now let's go ahead and pin down where all these things come from. We already have Elena pointing out that my constant value c from my quadratic equation in standard form is always the y-coordinate of the y-intercept. And so it looks like 7 is going to be the y-coordinate of the y-intercept. So my y-intercept comes from 0 comma c. In this case it's 0 comma 7. And I see it right there. Good. The axis of symmetry, right? The axis of symmetry I can also see in my quadratic equation. So the axis of symmetry comes from where MathWoman starts before walking to the right or to the left to get my x-intercepts. It looks like MathWoman would start at the -4, x equals -4 on the x-axis before walking to the right or to the left 3 units. Let's check. So the axis of symmetry here, I'll go ahead and draw in with a vertical line. If I could get a line to cut through the vertex. Oops. It looks like x equals, yes, -4 would cut right through that vertex. You guys see it? So x equals -4 is my axis of symmetry. In which piece of the quadratic formula, right, was that hidden? So let's go back and see where this -4 came from. -4 came from, -8 halves came from -8 over 2. So this came from opposite of b over 2a. Guess what? The axis of symmetry, which is also the x-coordinate of the vertex, is always given by the opposite of b over twice the value of a. So let's add that. So the axis of symmetry is x equals opposite of b over twice the value of a. That's always true. So if I'm in standard form for my quadratic equation, everything on one side is equal to 0, I can get the x-coordinate of the vertex or the axis of symmetry by taking opposite of b over 2a. Let's count out the distance between the axis of symmetry and the x-intercepts. So if MathWoman hops on the x-axis at the axis of symmetry, how far does she have to walk to get to an x-intercept? Well, let's see. Ready? 1, 2, 3 units. So it looks like 3 units is the distance that separates the axis of symmetry to the x-intercepts along the x-axis. Let's check the other direction. 1, 2, 3 units. Yes, that's right. And so it looks like 3 units is my distance that separates that. Where did that come from in my quadratic formula? Well, here's my 3 units that are walking to the right or walking to the left. That came from 6 halves, which came from root 36 over 2, which came from radical b squared minus 4ac all over 2a. So this second part, the second piece after the plus or minus, that's my distance number. Right? That's my distance number. All right, let's finish it out. My x-intercepts we already saw. That was -1, 0, and -7. Is that right? -7, 0. Where did those come from? Well, those are my solution values at the end, right? Those are my x equals solutions at the end, exclamation point. So I'll write that again. And lastly, the vertex. Well, we already know the x-coordinate of the vertex is always on the axis of symmetry. Therefore, my vertex, the x-coordinate is always given by x equals the opposite of b over 2a. Now, how did we figure out the y-coordinate of the vertex? Well, we'll plug that into my function rule y and evaluate it. So let's go ahead and determine the y-coordinate algebraically first. We'll go to my y function, which accepts input values that are x's, except everywhere I see an x, we won't put x. We'll put the x-coordinate of the vertex, right? My axis of symmetry. So plus 8 times x plus 7. And what is that? Well, my x-coordinate of the vertex is opposite of b over 2a, and we already did that. Opposite of b over 2a was opposite of 8 over 2, which is -4. So that comes from opposite of b over 2a in my equation. All right, that is opposite of 8 over 2 times 1, and that equals -4. We're going to plug that into my y equals equation and evaluate. Here we go. -4, -4, -4. Let's do it. -4.8 squared is 16. Plus 8 times -4 is -32. Plus 7. Combine like terms, I get -16 plus 7 is -9. Is that what you guys are getting? -9? Visually, how are we doing? Well, let's see. If we count it out, down 1, 2, 3, 4, 5. Looks like -4, -9 certainly matches my graphical appearance, and so -4, -9 are my coordinates of the vertex. That's pretty sweet. Let's go ahead and summarize our findings. So, in a quadratic equation, ax squared plus bx plus c equals 0, in standard form set equal to 0. x equals opposite of b over 2a will give me the x-coordinate of the vertex and the axis of symmetry. So if you're given an equation, all right, if you're given an equation, you can rearrange it in standard form and then get the x-coordinate of the vertex by evaluating x equals opposite of b over twice the value of a. That b squared minus 4ac, right, inside of a radical, closed radical, all over 2a, that second part of the quadratic formula, collectively, right, ended up being my distance number. That was the distance number that math woman walked to the right or to the left of my axis of symmetry along the x-axis before encountering the x-intercept. And so that's the distance from the line of symmetry to the x-intercept. If I put those two pieces together and walk to the left of the axis of symmetry and to the right of the axis of symmetry, I'll end up at the x-intercept of the graph. And so each of those x equals solution values, we already know to be the x-intercepts of the graph. The y-intercept from standard form is always 0, comma c. It's the constant value in my standard form quadratic equation set equal to 0. And lastly, the vertex, we already clipped in for you because there was a lot of writing. We know the vertex is on the axis of symmetry. So we know the x-coordinate that is opposite of b over 2a. That's the x-coordinate of the vertex. To determine the y-coordinate, we'll evaluate my function rule at that x-coordinate. So if x is the opposite of b over 2a, then f of opposite of b over 2a, that is the y function rule evaluated at x value of the vertex, will give me the corresponding y-coordinate of the vertex. So opposite of b over 2a paired with my function rule evaluated at opposite of b over 2a, that gives me the coordinates of the vertex. That's pretty sweet. Now we're ready for the super cool picture that puts it all together. As you know, a picture is worth 1,000 words. This is powerful. Let's take a look. So here's my standard form, y equals ax squared plus bx plus c. My vertex has coordinates opposite of b over 2a. That's my axis of symmetry, paired with the value of the function, right, at x equals opposite of b over 2a. If we're math women and we walk along the distance, root b squared minus 4ac quadratic over 2a, to the right, I get an x-intercept, a solution value. If math woman goes back to the axis of symmetry and now this time walks to the left, see my subtraction? There's walking to the left. We end up at a solution value, that's an x-intercept. And of course my constant value, 0, comma constant, gives me my y-intercept. So that picture is worth 1,000 words. We can see all the key pieces of my quadratic formula connected explicitly to the graph of the parabola, y equals f of x. That is awesome. All right, so let's go ahead and see if we can apply it now. Let's suppose that we have a new quadratic equation that's not all nicely set up in standard form for you. In order for the quadratic formula to work, we have to have this in standard form, everything on one side and set equal to 0. Is this in standard form right now? No. So we're going to go ahead and add over that 13x, subtract over that 1, and rearrange in standard form, ax squared plus bx plus c equals 0. Let's go ahead and do that now, please. So we'll add over that 13x. We'll subtract over the 1 and combine like terms. We get everything on one side and set equal to 0. Now and only now can we pick out our values of a, b, and c so I can substitute in the quadratic formula. Please be ready to share. Now that I've rearranged the standard form, what will I use for the value of a? What will I use for the value of a? Philip?
5.
5, thank you. So I'm using my green standard formula to generate that. What will I use for a value of b? Lynn? 13, thank you. What will we use for our value of c? Kennedy? Thank you. I can now plug those values for a, b, and c into my quadratic formula. And I'm going to go ahead and jump right to my x equals opposite of b over twice the value of a plus or minus the square root of b squared minus 4 times a times c closed radical all over twice the value of a. And substitute in my values for a. This time it's 5. Look at that. So we've got 5 in for my value of a in each case. Now we'll plug in our value of b everywhere that appears. So B is 13. We'll go ahead and put in 13 everywhere we see a B. And lastly, we'll replace C with -6. All right, guys, now we'll go ahead and evaluate my expression, and that'll give us our solutions x equals. So let's go ahead and do it. We'll hop in there and start doing some evaluating. So I've got x equals. Opposite of 13 over 2 times 5 is -13/10. Plus or minus, let's jump inside the radical. 13 squared is 169. Minus 4 times 5 times -6 overall is a positive 120, so plus 120. Close radical all over, 2 times 5 is 10. So x equals -13/10. It looks like I already see my axis of symmetry. My x-coordinate of the vertex, my opposite of b over 2a must be -13/10. Let's figure out my distance. The math woman's going to walk along the x-axis to the left or to the right to get x-intercept. So let's jump inside the radical. Here we go. 169 plus 120 is 289, and I believe that's a perfect square, so this should simplify nicely. All over 10. We'll keep going. So x equals -13/10 plus or minus, and let's simplify that square root of 289. I know you have calculators at the ready. This works out to an integer, doesn't it? What's the square root of 289? Is that 17?
Yeah.
Awesome. Thank you. So I'm seeing my distance number. I've got my axis of symmetry is -13/10. Then we're going to walk to the right, 17/10 of the unit. And then go back and walk to the left, 17/10 of the unit, and we'll get both of our x-intercepts, I should say. So let's go ahead and keep going. This can be rewritten then as two solutions. One of them is given by x equals -13/10 plus 17/10. The other one is given by x equals -13/10 minus 17/10. Let's see what that is. So in my first case, I get -13/10 plus 17/10 is +4/10. Is that what you guys are getting? So I'm getting 4/10, which is also 2/5. In the second case, I get -13/10 minus 17/10 is -30/10, which is equal to, that's much nicer, -3. Tell your partner what 2/5 and -3 have to do with the graph of my original equation set equal to 0. So this green line, right? What do -3 and 2/5, if anything, have to do with my original? What are those? Jacob? What do these numbers have to do with this green equation? The x-intercepts, right? The x-intercepts. So let's go ahead and verify then. Let's verify that with our grapher. So we'll go ahead and check with our grapher. I'm going to go ahead and rearrange the standard form. So we already added over. We added over my 13x. We subtracted over our 1 and set equal to 0. And then called that a function. Y equals 5x squared plus 13x minus 6. And so we went and go ahead and go to the grapher. So let's go ahead and grab that equation. I'm going to clear out this function. I'm going to up arrow and turn off my plot. And I'm going to zoom 6 to return to a standard viewing window. So I've cleared out my y equals menu. I've highlighted my plot 1 and pressed enter to turn it off. I want my plot 1 off. And I'm now going to enter my new equation. 5x squared plus 13x minus 6. I'm going to go ahead and look at a picture of that, and I'm going to see, right, I'm going to see if our x-intercepts Jacob told us about are in fact, right, -3 and +2/5. I can't see this window very well, so I'm going to manually adjust, and I'm going to go -6 and up until 2, and I'm going to go -25 to 10 and see if this is a better picture. So I'll go ahead and take a look at this graph. Ooh. So how can I check easily to see if my x-intercepts are -3 and 2/5 as Jacob suggested? Well, I could go and do second calculate 0 and see what it gives me. Or, since I already know what they are, I could do trace, input the x value, enter, and the cursor should jump on the x-axis. Either way is acceptable. In this case, since I already have an idea of what they are, -3 and 2/5, it's quicker to do trace, -3, enter. Voila! The cursor has jumped on the x-axis and paired that x value -3 with the output y equals 0. We know that is an x-intercept. I'm now going to enter 2/5. Trace, 2/5, enter. And the cursor jumps on the x-axis, pairs it with the y-coordinate 0. Did you ever see that? So we know that those are the zeros and we know we've done it correctly. Awesome. What questions do you have about the graphical connection? The graphical connection to the quadratic formula. Then let's go ahead and close it up for today. So we now need to know when is it appropriate to use the quadratic formula. So let's go ahead and add, if we have a standard form, y equals ax squared plus bx plus c. For today's closure, I'm going to go ahead and share with you, and we'll see this template again. When is it most efficient to solve the standard form quadratic equation by taking a square root directly, and without having to complete the square? Well, that's the same as before. When b equals 0, there's no linear term, so it's appropriate to solve by taking square roots. So that's appropriate when b equals 0. That means there's no linear term to contend with. There's no x term mixed in with our x squared. Now let's go ahead and consider the difference between completing the square for a solving method versus with our new quadratic formula. So solve by completing the square. Now b doesn't equal 0, so there is a linear term. So b doesn't equal 0. If b is even, a doesn't equal 1, and I can't factor. If those conditions are met, then I'm going to go ahead and complete the square. Notice how that's a lot of conditions, right? So b doesn't equal 0, which means there's a linear term and it's even, so that I can divide it by 2 to get my special number. A doesn't equal 1. Oh, I'm sorry. A equals 1. A equals 1 is what I'm after. I'm thinking ahead to a quadratic formula. I need a leading coefficient of 1 in order to complete the square, so a must equal 1. Sorry, make sure you fix that right now, please. That was my mistake. A equals 1. And I can't factor it, then I'll go ahead and do complete the square. Lastly, if b doesn't equal 0, but it's odd, and a doesn't equal 1, like it's 2x squared or 3x squared, and I can't factor, then I'm going to go ahead and use quadratic formula. So let's go ahead and summarize that. Again, b doesn't equal 0, but is odd. And or a doesn't equal 1, and I can't factor, then I'm going to go ahead and do quadratic formula. These would be good reasons, right, as to why you'd employ certain methods. Now, we have a nice chunk of time here, right, that we tried to structure in so you could be practicing your solving quadratic equations effectively. So we have a two-pronged assignment. We've got a solving equations worksheet. Number 2, I want you to work on that first. And we also have a book assignment and reading questions. But first, I'd like to share with you our clip of Emily, our young Emily, who guarantees, right, that you guys can memorize the quadratic formula because she can. So let's go ahead, and I'm going to stop the recording now.